We plugged it in, we worked it out. When we're going to find the domain, we want to look at the domain of each individual function. And then for our composite function, we want to look at the domain of the first function and say, okay, are there any restrictions on it? If there are, then we need to know when is g of x equal to those restrictions. There aren't any on this one, so our domain of f composed with g of x is going to be the same thing. It's going to be from negative infinity to positive infinity. Our final answer we're going to write in interval notation there. But I'm using set notation until I get to the final answer because I'm going to need just regular numbers. I don't really need all of the infinities and that sort of stuff for the not final answer parts. Okay. So this one with no restrictions is super easy. You don't have to think about it. We look at that and remember the red flags back from chapter 3 about domain. There's got to be an x in the denominator or a square root or some sort of radical in the problem for there to be some red flags and restrictions on the domain. Look for those things. If they're there, we're going to have to address them as we go to do these domains. So let's look at taking that particular function composition and doing a little bit of stuff with it because that's one of the things that happens. That's example E. Example E, if we did f composed with g of 2, where f of x is the same function, 2x squared minus 3, and g of x is still 4x. Those are still the same. We're using the same ones. And they wanted us to find f composed with g of 2. Since we already have the composite function, that means, all I got to do is take 32, plug in a 2, and work that out. And that would be 32 times 4 minus 3, 128 minus 3, which is 125. So you're just taking the composite function and plugging in x, just doing function value again. Now, here's where if you didn't have that composite function, you could take that and work it out without having to find that composite function, because sometimes finding the composite function is pretty difficult to do. So if they only gave you a function value problem, a lot of times on like the final exam, they'll give you 2 pretty difficult functions and ask you just to find the composite function value. And instead of taking all that time, because I got a 2-hour time limit, instead of taking all that time to work on the composite function, if I've got a number that I know I'm going to plug in, then I can work just from that. So the way that you would need to do that is start with the second function and plug in 2 for x. So 4 times 2, we get 8. And then the way function composition works is that you then take that answer and plug it into f. Okay, so then we would do f of 8. We get 2 times 8 squared minus 3. So that'd be 2 times 64, which is 128 minus 3. We get the same answer, but we didn't have to go through the work of finding the composite function, even though we'd already done it for this one, so it made it easier to do. But if the composite function is pretty difficult and all they really want you to do is get a function value, just plug the number into the second function, get that answer, plug that answer into the first function, and you'll get there pretty easy. All right, let's step it up and do a more difficult problem for function composition. Let's say f of x is 1 over x plus 5, and g of x is 4 over x minus 1. Okay. So this one is quite a bit more difficult. Let's find f composed with g and the domain. Okay. All right. So f composed with g of x is taking the g of x function and replacing x with all of that. So we got fractions inside of fractions. That's what makes this one tough. So 1 over 4 over x minus 1 plus 5. And that looks ugly because you got a fraction inside of a fraction. So you got to fix it and make it simpler, okay? Or make it more complicated so we can simplify it is basically what that boils down to. So in order to add these two fractions that are on the denominator, I need to have what in order to add them? A common denominator. Since this one has x minus 1 as a denominator and that one has a 1 as the denominator, the common denominator would just be the product of those two, which is just 1 times x minus 1. So we're going to multiply this one by x minus 1 on top and bottom to get a common denominator in that part of the problem. So that'd be 4 over x minus 1 plus 5x minus 5 over x minus 1. That's what we now have for this problem. We can simplify the bottom part because we got like terms, 4 plus negative 5. And so that's going to simplify to be 1 over 5x minus 1 over x minus 1. So we have a fraction inside of a fraction. I'm dividing by this fraction. And if we think back to rules for operations with fractions, dividing by a fraction is the same thing as multiplying by its reciprocal. So what's the reciprocal of that fraction that I've got in parentheses there? Yeah, so we really have 1 times x minus 1 over 5x minus 1. And 1 times that fraction is just going to be that fraction. F composed of g of x equals x minus 1 over 5x minus 1. All of that work, and that's what we end up with. Okay. Now, finding the domain, a little bit more difficult here. We need to look at the domains of each individual. The domain of g of x. What are the restrictions on the g of x function that we started with? How do we find that? So g of x was 4 over x minus 1. To find the domain of g of x, we take what part? Where's the red flag? It's in that denominator, right? Can't have an x in the denominator. We set that x minus 1 equal to 0. Yet x cannot be 1. So that's a restriction. If we go and then look at the domain of f of x, the original function for f of x is 1 over x plus 5. The denominator is where the problem lies when it comes to domain. So we set x plus 5 equal to 0. Yet x cannot be negative 5. Now here's where it gets a little sticky, because your restrictions are not just 1 and not just negative 5. What we've got to decide is we've got to answer this question: where is g of x equal to negative 5? Because g of x is what's replacing this x, right? When we did our composition, that's what we did. We replaced this x with the whole g of x function, okay? So we got to know where is g of x equal to negative 5. And that negative 5 is coming from this restriction. That's the reason we're asking that question. So to answer that question, we take the g of x function, 4 over x minus 1, and say, okay, equals negative 5. We set up an equation and say, okay, if that we need to know where it's equal to that, we just set it equal to it. and work it out. So when I put that over 1, it makes it look like a proportion. Y'all remember cross multiplying to solve proportions? Back in probably a geometry class, you did that quite a bit. So 5x minus 5 is equal to 4. You get to add 5. 5x equals 9. Is that right? Nope. That's a negative 5 over there, isn't it? So that's a positive 5x plus 5 equal to 4. And then move it. That makes a difference. 5x equals negative 1. Right? And then that's negative 5x. And then divide by negative 5. Made all kinds of sign mistakes on that, didn't I? So that makes it 1/5. So there's the restriction that occurs because we're taking g of x and putting it into f of x. So the restrictions for the composite function, so the domain of f composed with g of x is all x's as long as x does not equal negative 1, or excuse me, that was positive 1. Let's look at, yeah, right here, positive 1 and positive 1/5. The negative 5 is not part of the restrictions, okay? Because we replaced that x with the g of x function, okay? That's why that restriction, it affected the restrictions of the composite function, but it's not one of the ones that we're going to use, okay? And then we need to write that in interval notation for the final answer of that. So interval notation for that. So we go from negative infinity up to 1, and union from 1, oops, not to 1. 1/5 smaller, isn't it? 1/5 would come first. 1, union, 1 to infinity. That's a long interval notation. So here's our set notation on top there. A lot easier to write there. And then there's the interval notation. Be able to bounce back and forth between those two different notations there. So when we look back at our composite function, look at the denominator. If I had set that equal to 0, what value out of our domain would it have gotten? I set 5x minus 1 equal to 0. That's the 1/5, right? And where we can lose that 1 in the numerator, it's not a red flag if it's in the numerator. That won't always show up. You've got to find the domain of the second function and then apply the domain of the first function. That's kind of how the process that you need to go through. And if you look at your composite function, be careful to not just strictly go by it. A lot of times it will take care of things, but if it were to simplify at any point, you may lose some things that should be in your domain that are just, they got canceled out in the simplifying step. So you've got to be careful about that along the way. Let's look at another one and see if we can kind of nail this down. F of x is equal to the square root of x plus 3, and g of x is equal to 2x plus 5. Okay. Let's find the f composed with g and the domain. A lot of time talking about that. So f composed with g of x and then the domain. So we're doing that same order of things. So we're taking g of x and putting it into the f of x function. So the composite function, this one's actually not too bad because there isn't a whole lot going on with it. It doesn't have the fractions in there. It's just got the big square root. So I'm going to replace x with 2x plus 5, and then the plus 3 is still in there. And then I'm just going to simplify. So be 2x plus 8. And there's my composite function, f composed g of x. And I found the composite function. Now the more difficult thing is to find the domain of that. So let's get our domains. The domain of g of x. Remember, we start with the second one. Are there any restrictions on g of x? Any red flags coming up for g of x? No, it doesn't have any fractions. It doesn't have a square root in it. So it's all x's as long as x is a real number. So no restrictions on g of x. F of x, however, you've got a restriction. How do we handle a square root to find the domain? Well, how do we tell the domain of f of x? What is the domain of f of x? What kind of numbers can we take the square root of and not have something weird happen? Positive numbers, we can take square roots like positive 9, positive 64, that sort of thing. That makes it work out right. So positive numbers are good to take square roots of. What other number is good to take square root of? And probably the easiest to take the square root of? 0. Square root of 0 is 0, always, right? So we take what's inside of the square root, x plus 3, and set it greater than or equal to 0. We solve that, and that's going to get us the domain for f of x. So that'd be x has got to be greater than or equal to -3. So that's the domain of f of x. So I need to find out when is g of x going to be greater than or equal to -3. That's what I've got to find out. So I'm taking 2x plus 5 and setting it greater than or equal to -3. Divide by 2. All right, so we got x's are greater than or equal to -4. So the only parts that matter when it comes to the domain of the composite function is that part and this part up here. This middle piece, the f of x domain, does not have any, it doesn't show up in the domain of the composite function, okay? The domain of the second function listed and then the composite function, those are the ones that are going to show up. So domain of the composite function of f composed of g of x is going to be all x's as long as x is greater than or equal to -4. There aren't any restrictions up here, right? With the g of x function, it was all real numbers. There were no restrictions. So there's nothing extra to add other than that, okay? So this x is greater than or equal to -4 in the interval notation, be -4 to infinity. So there's our domain for that composite function. Let's take it the other direction. Let's go to g composed with f. Because a lot of times they'll just turn it around and do, okay, we got f of x is still the square root of x plus 3, and g of x is still 2x plus 5. And let's find g composed with f of x and domain. So G composed with F means we're taking all of this and throwing it into that. The second one into the first one. So that's going to be 2 square root of x plus 3, and then a plus 5 on the outside. There are no like terms. You can't distribute into a square root. So there are no like terms to put together. This is going to be your composite function. Actually, pretty easy on that one. Okay. When we look at our domains, again, we're going to start with the second one listed in the function composition statement. So the domain of f of x, we know x plus 3 has got to be greater than or equal to 0, and x has got to be greater than or equal to negative 3. And then the domain of g of x, we already know that that's all real numbers. All right, so if there are no restrictions on the first function listed, then the only restrictions we have to worry about are from the second function. So the domain of the composite function, G composed with f of x, is x is greater than or equal to negative 3. So all x's, as long as x is greater than or equal to negative 3. In interval notation, negative 3 to infinity. Because there were no restrictions on that, we didn't have to do any extra work. And that's kind of nice when that happens. We don't have to do some extra work there. So restrictions on the second function listed in the composite statement, and the restrictions when you apply the first restrictions. Let's look at another one, maybe one that's slightly more difficult. I don't know. I think it really is, but maybe you do. H of x is x squared minus 5x plus 7. And then k of x is 3x over x minus 2. All right, so this one, let's find h composed with k and the domain. All right, so h composed with k. So that means we're taking this and putting it in for x in that function. So we have h composed with k of x. So 3x over x minus 2 squared minus 5 times 3x over x minus 2 plus 7. So a good bit of algebra going to happen here. Try to make it as simple as possible. So when I square 3x over x minus 2, I'm going to square the numerator, and that'll be 9x squared. But on the denominator, I'm just going to write it as x minus 2 squared instead of multiplying it out, x minus 2 times x minus 2, because that's just going to make it longer. Bless you. And then the second fraction, I've got 5 times 3x would be 15x. And then it's over just 1 x minus 2. And that's 7. Since everybody else is a fraction, he feels left out, so let's make it a fraction as well. Okay. So I want to simplify that. So I've got addition and subtraction of fractions. So I want to find a least common denominator for those 3 fractions. So notice that the factors here, that's a x minus 2. It's 2 of them. This is 1x minus 2. And then this is just a 1. So the common denominator is going to be x minus 2 squared, which works out pretty nice because that means I don't have to do anything to this first fraction at all. Okay, so the first fraction is just going to be 9x squared over x minus 2 squared. The second fraction, it needs another x minus 2, so I'm going to multiply x minus 2 on top and bottom. The third fraction needs x minus 2 twice on top and bottom. So that's going to give me 15x squared minus 30x over x minus 2 squared. And then I'm going to have to multiply out the numerator here. X minus 2 squared is x squared minus 4x plus 4. And then I'm distributing a 7 to that. So that's 7x squared minus 28x plus 28 over x minus 2 squared. A lot of simplifying to do here. I'll put parentheses around that because that negative sign has to distribute to those. So start simplifying it out here. We got 9x squared minus 15x squared. That'd be negative 6x squared plus 7x squared is 1x squared. And then we have a positive 30x and a negative 28x would be positive 2x. And then we have a positive 28. So all of that to get down to that one single fraction at the end. Change that to a color you can see a little better. Okay. Now, I would try to factor the numerator to see if I could get something to cancel out to make it simplest terms. But there's nothing that multiplies to be 28 and adds to be 2, so I know I can't factor it. So you have to try to do that to see if it'll simplify. It doesn't in this case, so that means this is our composite function, h of k of x, h composed of k of x. So there's our composite function. Now we got to do the work of finding the domain of that. Okay, so the domain, let's get the domain of k of x. So k of x was 3x over x minus 2. How do you get the domain of that? X minus 2 equals 0. X cannot be 2. Let's get the domain of h of x, which was x squared minus 5x plus 7. That's a quadratic. What do we know the domain of quadratics is? It's all real numbers because there's no red flags. There's no square root. There's no x in the denominator, so we know we don't have to do anything with that. Now, here's the beautiful thing. There are no restrictions on the first function in the composite statement. Okay, the composition statement has h of x listed first. Since there are no restrictions on that, I don't have to do any extra work. The only restriction I have is the x cannot be 2 that came from the second function. So the domain of my composite function, h composed with k of x, is going to be x cannot be 2. And then the interval notation would be from negative infinity to 2, union from 2 to infinity. If there had been restrictions on the first function in the composition statement, I would have to set the second function equal to those restrictions. That's how you find those things, especially when you're dealing with rational expressions where things could cancel out and simplify out. You could lose part of your domains if you simplify something out. So you got to be careful about that. You can always kind of look at our composite function, and look at the denominator. We notice it's the only factor in the denominator is x minus 2, so that would be the restriction that's on that composite function. But you've got to be careful, especially with the rational ones. Something may have canceled out if you only look at the composite function. You really theoretically should always do it the order that I've shown you. Sometimes there's shortcuts, but they don't always work. So just be careful of that. All right. Let's go to the next section. A little easier on the next section, I believe. This one can be somewhat confusing. 6.1 was. So 6.2 is a little better. 6.2, 1-to-1 functions and inverse functions. All right. What makes something a function? What are the rules for being a function? We talked about this back in chapter 3. In order to function properly, never repeat what? What values cannot repeat and be a function? X values cannot repeat. One-to-one functions are functions to begin with, so their x's don't repeat. X's can't repeat and y's can't repeat. You're one-to-one, that means for every single x, there's a single y that goes with it. Okay? You guys are all nursing majors. You know the way chromosomes work, it's supposed to be one, an X and a Y go together. If that ever gets out of kilter, things go wrong, right? Things change. So one-to-one functions, the same idea, okay? It's got to be a function, so X's can't repeat to begin with, but to be a one-to-one function, the Y's can't repeat either. So it's individual ordered pairs along the way. So one-to-one functions map one X to one Y to one X. So it goes both directions there. It's one-to-one, okay? And let's just start with the that game, kind of like we did with chapter 3. Is the relation a one-to-one function? Example A, we'll do a mapping to start off with. -3, 1, 6, 8, 7, 5, 8, 10. And then the mapping is you just draw some lines to represent the ordered pairs. So -3 to 10, 1 to 7, 6 to 8, 8 to 5. Okay. So there we have a function represented there because none of the x's repeat, but there's also no repetition of any of the y's. So this is a one-to-one function because it doesn't repeat x's, it doesn't repeat y's. Is this a one-to-one function? No. Is it a function? It is a function, but it's just not one-to-one. Okay, so this one would pass the rules for function because none of the x's in the domain repeat, but we've got a repetition of the 3 and the y values that repeat. So this is not one-to-one. All right. Easy speasy. Let's go to some graphs. What was the test to decide if a graph was a function? So we got just a coordinate plane is all I'm drawing here, and then something like that. Is that a function? What's the test that we used? Yeah, that vertical line test. Yeah, vertical line test. We could check that for vertical lines. If we drop a vertical line anywhere on that, it only touches in one place anywhere we drop it. To be a one-to-one function, you got to pass the vertical line test, but then you got to also pass a horizontal line test. Okay, so horizontal line test. Same rules as the vertical line test, but it checks for repeated y values is what it checks for. Vertical line test checks for repeated x values. Horizontal line test checks for repeated y values. If I drop a horizontal line on that thing, how many times does that red line cross the blue? 2 times. So that right there says, hey, that's got a repeated y value, and that does not make this one-to-one. So this is not one-to-one. So to be a one-to-one function, you have to pass the vertical line test and the horizontal line test. So D. Here's just another coordinate plane here. There's a nice polynomial graph there. Does that pass the vertical line test? Yes. Does it pass the horizontal line test? Yes. So that means it is a one-to-one function. So yes. 1, 2, 3. Good to know. Now, what if they just give us an equation? What example E? Sorry, don't know my alphabet today. 3x squared minus 5x plus 7. How can I decide if that's a one-to-one function? That happened. Graph it. Yeah, that's absolutely the best way to do that. So I'm going to go to y equals, almost had the right one there. 3x squared minus 5x plus 7. And hit graph. Oh, we see a parabola. And does that pass the vertical line test? Yes, but does it pass the horizontal line test? No, so that is not. So checking a graph to get an equation. That's the easiest way to tell if something's one-to-one or not. Okay. Now, one-to-one functions, what's the point? Well, go back to the title of the lesson, talk about inverse functions. So one-to-one functions have inverse functions. Okay. Equal functions can have inverses, but their inverse may not be a function. Okay. So there are like like that parabola there on example E. It's a function. We could find an inverse of that, but the inverse isn't necessarily a function. A one-to-one function is pretty special because the original is a function and its inverse is also a function. Okay, so that's why they're special, and we spend a whole section talking about them. So one-to-one functions have inverse functions, so they meet the criteria backwards and forwards of being a function. That's kind of what that means there. So what does an inverse function do? An inverse function interchange the domain and range of a function. The way that I always kind of layman's term here, swap x and y. That's the short way. That's the way I always remember it. Inverses, swap x and y. Okay. So when you talk about a function, maybe in its most basic form, example F, let's say we had a function, and its most basic form would be just like a list of ordered pairs. Something like -3, 6, -1, 7, 2, 13, and maybe 5, -8. That's a one-to-one function, just a set of ordered pairs. There's no repeated x's, there's no repeated y's. So it is a one-to-one function. The inverse of that function interchanges the domain and the range. So the notation that we use looks like a little -1 exponent. So F inverse of x. And you just swap the ordered pairs around. 6, -3. 7, -1. 13, 2. -8, 5. The inverse swaps the domain and the range around. Really, really simple when it's just a set of ordered pairs. Maybe not quite as simple when it's an equation. We're going to get to that. Okay. So swap x and y. That's going to be important. Okay. So let's look at maybe the instructions were find the inverse. All right. So example G. Let's look at a linear function. F of x is equal to 6x minus 7. Something real simple to start with. Okay. So that is a function. It's a linear function. We know what that looks like. If we graph it, just to verify that it is a one-to-one function, we do 6x minus 7, and that passes the vertical line test, and it passes the horizontal line test. So we know it's one-to-one. Okay, so we're just going to go with that assumption that that's what they're going to be, and then we're going to find the inverse function. So the way that you want to do that, give myself a little more space here, is f of x. What does f of x mean? It's the same thing as y, right? So this is really y equals 6x minus 7. So you're thinking that in your head. What does an inverse do? It swaps x and y. So with your equation, do that. Swap x and y. X equals 6y minus 7. Okay? So we swap x and y and then get y by itself again. Just solve that new equation that's in red. Solve it for y. So I'd add 7. X plus 7 is equal to 6y. And then I divide everybody by 6. Everybody. And then I've got y by itself again. I have y equals 1 over 6x plus 7 over 6. The last thing I need to do is write it in function notation. So I have found the inverse. Once I get y by itself, I have found the inverse. So the inverse notation would be f inverse of x equals 1 over 6x plus 7 over 6. If you wrote x over 6, that's the same thing. I just like to write the fraction in front of the x out of habit, I guess, because we talk about slope and stuff in algebra 1 and stuff. That's where I'm at. Okay. Are there any restrictions on this domain? No. No x's in the denominator, no square roots there. So no restrictions on either the original or the inverse function on that one. So, but again, that's the process. You're going to swap x and y, get y by itself again. So let's do a little tougher problem besides that one. That's too easy. It's not college level stuff. So let's do one like this. F of x is equal to 2x plus 1 over x minus 1. And then they say out here to the side, they say x does not equal 1. Why do they say that? Can't divide by 0. So that's a restriction on the domain. That's all they're telling us there. Hey, here's a function. There's a restriction on the domain if you didn't know. That's what they're trying to tell us. All right. So we want to find the inverse function of this. So again, f of x is the same thing as y. And this one's a little more complicated because I have x in 2 places, but I swap them just the same. 2y plus 1 over y minus 1. So we really step it up on this one. This is a big jump, probably. Maybe too big. I'm not sure. We'll see. All right. Now, how can I get that y minus 1 out of the denominator? Because, I got to get y back by itself, but I got a y in the denominator, so I need to get it out of there first. Yeah, if I multiply by y minus 1, they'll cancel each other out like that, right? And then I'm going to distribute and get xy minus x equals 2y plus 1. I need to skip a line here. My handwriting is not so great today, for whatever reason. How to practice, I guess. All right, so that's still pretty ugly. Got some y's on each side and some x's on the other side there. That's fun. So let's try to get all the like terms together. So what are the like terms in this problem if I'm trying to get y by itself again? I need all of the things that are not y at all together, and anybody that's got a y needs to be together, don't they? Okay, so I'm going to do that. I'm going to move the x by addition, and I'm going to move the 2y by subtraction. So that's going to give me xy minus 2y is equal to x plus 1. This is where the your algebra ninja skills come in real handy, because when I look at the left-hand side, what do both of them have? xy and 2y. They both got a what? A y, which is also called a common, starts with an F, ends with an actor. Common factor, right? So can I factor a y out of those? Mathematically, it's legal to do that because they both have it. So if I do y and then x minus 2, I'm almost, now the y is starting to separate a little bit. Okay? What's going on between the y and the parentheses? They're multiplying. The opposite of that would be division. And the part I want to leave by itself is y. So I'm going to divide by this x minus 2. Those cancel out. Hey, there's y by itself, x plus 1 over x minus 2. And I need to go into function notation again. So f inverse of x is x plus 1 over x minus 2. What's the little notation I need to make about the domain? X cannot equal 2. That's a pretty tough one because of that little ninja trick there with the factoring out the y. So it makes that a little tough, but doable. Okay. Now, keep that in mind. So make sure you put a star by that example. You can go back to it because those come up. Maybe not often, but when it does come up, that's the only way to do it. So make sure you put a star by that example so that you know you got that. Let's go to one that's maybe a little easier, just because it doesn't have all that factoring and junk in it. So g of x is equal to x squared, and the restriction is that x has got to be greater than or equal to 0. The reason that I do that is because if I don't, then I'm not going to have a one-to-one function. That domain restriction creates a one-to-one function out of that, because the graph of x squared normally is this parabola that looks like that. But if I restrict the domain to only x's that are greater than or equal to 0, it's only that half of the parabola, which then passes the vertical and the horizontal line test. So that's the reason they've got that restriction there, even though there's no red flag really in the problem to start off with. They do that so that it makes a one-to-one function. Now, let's go to find the inverse of that. So again, how do we find the inverse? Swap x and y. So I'm just going to skip that step and go straight to x equals y squared. How in the world do you get rid of squared on a y? How do you unsquare something? Square root. Here's the only problem. If I put a square root into a problem, when I'm going to solve it, what do I have to put in front of it? Remember when we were doing quadratic formula? Not the I, plus or minus. Because you don't know if it's positive, what that x is, you don't know if it's a positive 8 or a negative 8 if x were 64, right? So you got to have that plus or minus. Now, here's where the restriction on the domain helps us out. What kind of numbers are the x values in the original problem? Positive, right? So which side of that do we really need? The positive side, because that's the side we started with. So that's the only side we want to finish with. So the final answer here is F, or G inverse, F, because we use G, equals plus or minus, no, positive only. We don't need the minus, because remember this restriction told us that, square root of x. And then we're going to say x has got to be greater than or equal to 0, because we're only dealing with positives. If the problem had started with the restriction of that, which side of the square root would you use? The negatives, because it started with negatives. Okay, so that's kind of one of those weird things that can happen there. All right. Now, the next thing that we talk about in this section, and one of the last things, is verifying inverses with a couple of different methods. Okay, so the first way is going to be algebraically. So verifying inverse functions and we're going to start algebraically. Algebraically. I always thought that was a fancy word. I can't even spell it. Algebraically. Algebraically. All right, there, algebraic. Glad that's not a vocabulary word this week for second grade. Do it. All right, so algebraically. So algebraically, what happens is it's based off function compositions. Okay. If f composed with f inverse of x equals x and f inverse composed with f of x equals x. Those are two different statements, but they both got to be true. Then f and f inverse are inverse functions. And the notation makes it a little crazy, but because we're using the inverse notation there. But that's the definition that our textbook uses. So I want to try to be somewhat consistent with it. So if we take two functions and we do composition with them and we get x back, then they're inverses of one another. That's what that says. Big picture of it is what it says. So let's take a couple of functions and decide, are they inverse, or prove more specifically, we're proving two functions are inverses of one another. So what letter we're on here? J. F of x is equal to 2x plus 3. G of x is equal to 1/2 parentheses x minus 3. Okay? We're going to prove or disprove that f of x and g of x are inverse functions. So we're going to do f composed with g of x. We're not worried about the domain of these. We're just trying to algebraically prove or disprove that they're inverses of one another. So if I'm going to do function composition, so this is the tie together between section 1 and section 2, I'm going to take the g of x function and replace x in the f of x function. So I'm taking 2 parentheses 1/2 parentheses x minus 3, close those parentheses up, plus 3. And I'm going to work this one out and simplify it and see if I get x. So 2 times 1/2 is 1. 1 times x minus 3 is x minus 3 plus 3. Hey, that looks promising. So it checks in that direction. Let's go the other direction. G composed with f of x. If on a test they're asking you to verify that they're inverses of one another, you do it this direction and get x, they're inverses. If you were asked to prove that things are inverses, you have to show both directions. But as far as the test goes, you don't really have to do both directions. I want to show you both directions here because you may find that one direction is easier than the other based on the problems. Okay, I think G composed with F is a little easier. It makes more sense to me anyway. 1/2 parentheses 2x plus 3 minus 3. That seems easier to work out to me than the first one did. So this is probably the direction that I would have chosen. 3 minus 3 cancels each other out. 2x, half of 2x would be x, right? They are inverse. F of x and g of x are inverses. That's what we found out by algebraically. Function composition can be used to prove two functions are inverses of one another. Okay? Not incredibly difficult, but algebraic. Let's look at okay. F of x, x to the third power minus 27, g of x, the cubed root of x minus 3. Okay, so getting a little fancy here with the roots and the powers and all that fun stuff, but still, same idea. So we're going to do function composition to either prove or disprove that they're inverses of one another. So I'm going to go f composed with g of x. I'm just going to go that direction first because I think it'd be easier to take this monster and put it in there than it would be to go the other direction. So that's the direction I'm starting with. So I'm taking the cubed root of x minus 3, and then I'm putting it in for x, so that means I'm going to cube that, minus 27. What happens when you cube a cubed root? They negate each other. They cancel each other out. So this and this cancel each other out. Leaves us x minus 3 minus 27, which is x minus 30. That is not plain old x, is it? It's got something else with it. That right there says, oh, no way, not inverses. I don't have to try the other way. I know it didn't work, okay? So if it Comes back to X there. The other direction is a kind of a checking point. It's a verification out of that. But if you come out of that and you don't have plain old X, they're not inverses of one another. Okay. So algebraically, it's doing function composition. That's how you can verify that two functions are inverses of one another. The other way is graphically. Graphically, inverse functions reflect across the y equals x line. Okay. So let's look at an example of that. Let's say f of x is equal to 2x plus 3, and g of x is equal to 1/2 x minus 3. What do we know about those? That's from a previous example. Are they inverses of one another? If you look back to example, example J, those are the same two equations. Let's verify it graphically. Graphically, I'm going to go to my graphing calculator, and in y1, I'm going to put in 2x plus 3. 2x plus 3. In y2, I'm going to put in the other equation, 1/2 parentheses x minus 3. In y3, I'm going to put y equals x, because that's the line they're supposed to reflect across. Okay? I'm going to hit graph. There's the first one. There's the second one. There's my reflection line. Look at these equations. The blue one is the 2x plus 3. It flips right across this line, and you know, if you folded this along the black line, they would match up perfectly out of that. Notice where they cross on that line too. Okay, so if they're going to cross, they'll cross on that line. Okay, so we can see the reflection there. Graphically, for one like this, it's super easy to see. But as they get more complicated, it's harder and harder to see, or as they spread out more, it's harder to see. So this is what it looks like graphically. I'm going to copy and paste that to my notes. All right. All right, let's look at one that's maybe not quite as wonderful out of that. So f of x, let's do x plus 4 squared. And the restriction is x is greater than or equal to 0. And then g of x is the square root of 4 minus x. So we got to be able to graph these things with our calculator. So that's just going to be tough, right? So my calculator, go to y equals, and in y1, I'm going to put x plus 4 squared. Then I'm going to put another set of parentheses. I'm going to put that restriction that x has got to be greater than or equal to 0. So to get greater than or equal to, I'm going to hit second math, and then go down to number 4, put a 0, and then close those parentheses. And then the next fraction or problem that I'm doing is the square root. So I'm going to open up a set of parentheses, and I'm going to put square root of 4 minus x. Then I'm going to close those parentheses, and then I'm going to put another one of those x is greater than or equal to 0. So x second math greater than or equal to 0. And I'm going to hit graph. See if I did it right. I think I didn't do that right because the blue one never showed up. Let me put a set of parentheses in here. I forget the syntax sometimes on this stuff. Second, insert parentheses. See if that works. I'm going to get, don't get any blue stuff there. X minus, or it's X plus 4 squared should be a parabola. 4 units to the left. Where is it at? Oops. Calculator. 6. I know why. My restriction. My restriction shouldn't be greater than or equal to 0. It should be less than or equal to 0 because that moves to the left. I should have did X minus 4 like I had originally written. I tried to change it up. Let's do that. So I'm going to change that on my y equals to a less than or equal to instead of a greater than or equal to. Second math, less than or equal to is number 6. And now hit graph. There we see what's happening there. Okay. Now, do those reflect across that black line? Obviously not. Right. So seeing the reflection, if they're close together like that, it's pretty easy to tell one way or another. If as the further the functions get spread apart or the more complicated the functions get, the tougher it is to see it graphically because you're really not verifying anything. You almost have to have ordered pair to ordered pair relationship or the X and Y swapped out of that. So as they get a little bit more complicated, it is the algebraic is probably more powerful. But if you just were given on a quiz or a test, are these functions inverses of one another? My first check would probably be graph it and see if I could tell that way. If I was unsure graphically, then I would go to algebraic. Okay, that was be my kind of strategy for going across this kind of stuff is start with graphically. If you can't tell, then go algebraic on that. Okay, be able to find the inverses. Remember, just swap X and Y, get Y by itself again, and you got it there. So sections 1 and 2. This week, I gave you the packets that have the regression and the rational things. Those are due November the 4th, which is 2 weeks on those. We will meet again next week. We'll do the next 2 sections in Chapter 6, and I'll put quizzes out for 6-1 and 6-2 this week for you to do. And we'll mosey our way through the rest of this semester. Make it through Chapter 6. Chapter 12's cake. Okay. The first 2 sections of Chapter 6 are the hardest ones, I believe. So.